Okay, everybody. So this week we're going to be trying to tie together what we learned with t-tests, what we learned with regressions, into this new concept of an ANOVA, or analysis of variance, and see how it all fits together. So to update you on where we are, we're down here in the parametric tests for categorical independent factors. We learned how to compare 2 with the t-test, and now we're going to learn what to do when you have 2 plus independent factors or 2 plus levels that you want to compare, and for that you'd end up using an ANOVA. So what's this problem with more? So last week we learned that t-tests are a great way to determine if 2 samples come from populations with different means, with the null hypothesis being that they're from populations whose means are equivalent, and the alternative hypothesis that they're from populations that have means that are different. But what happens if you have 3 samples, or 4, or 100, or 1,000? You could compare each group to each other group with the t-test, but it has some drawbacks. Number 1, it's a lot of work. You'd be doing 3 t-tests for 2 samples, 6 t-tests for 4 samples, 10 for 5 samples, 4,950 for 100 samples, and a lot more for 1,000. And that's not just more work. Your chance to commit a type 1 error goes up as well. So say you have an alpha of 0.05. Well, for 3 tests with an alpha of 0.05, your ultimate alpha for all of those tests would be 0.14. For 100 tests, your alpha would be almost 0.99, which is basically telling you nothing. So your chance of committing this type 1 error goes up and up in a way that is, we kind of covered back when we learned probability, right? You're multiplying 95% chance of getting it right, 95% chance of getting it right, 95% chance of getting it right over and over again, and that eventually drops you down to basically no chance of doing it without an error. So how can we tell if any of the groups are different? It's one thing to go and compare every single group and try to figure out which groups are different from which other groups. But what if we had a test that just asked, okay, the null hypothesis is that everything is the same, and the alternative hypothesis is that just one of any of these differs from all of the rest. That is what an analysis of variances, or ANOVA, is. Its null hypothesis is that everything is equivalent, and its alternative hypothesis is that one of these is not equivalent, or many of them are not equivalent to all of the others. So it's going to figure out how much variance is coming from within the groups and compare it to how much variance is between the groups. And this will sound familiar because we did it in some weeks past. And generally, if the variance between groups is greater than the variance within the groups, then you'll reject the null hypothesis and you'll think that one of these is different from all the rest. But importantly, ANOVA does not tell us which group is different. It simply tells you that one likely is. So after you find an ANOVA telling you, okay, one of these groups is different, then there's some specific tests that can parse those rather than having to do all these t-tests, and we'll go over one of those in the exercise this week. Okay, so what is this within versus between in an ANOVA? Remember back in Module 7, we calculated the ratio of within versus between variances. And this ratio is the foundation of an ANOVA. And so you've probably seen an F statistic before. We're going to tie F statistics in with R squared and p-values this week. So an F statistic is simply the ratio of your between group variance over your within group variance. We're giving it a name. That name is F. A bigger F means that the variance, there's more variance between the groups than there is within the groups. And thus, a bigger F will give you a higher likelihood of rejecting your null and saying that there is indeed a difference in this particular sample. And more specifically, an F value of 3.3 per se would indicate that the between group variances are 3.3 times the size of the within group variances. So you're getting information about the differences between and within built into this ratio. Okay, so how do we calculate this mystical F value? Well, we move back to our old friend, the sum of squares. So these here, I'd like this illustration of between group variation. If you had these three group populations, your between group variances is shown here with these black lines going to each of the means, and the within group variances are shown here with these black lines going to each of the groups away from the mean of group 1, the mean of group 2, and the mean of group 3, right? So this is the distance of the means away from the grand mean, which is in red here, which is the mean of all of them. And then these black lines here are the distance away from the mean of this group, the distance away from the mean of this group, the distance away from the ones of this group. So this is a good illustration of between group variation and within group variation. And I'll show you some more pictures as we go. Okay, so let's talk about R squared and F, because last week we learned about fitting a line to data. We learned about our sum of squared residuals and how they're useful for fitting a line y equals mx plus b to some data points. So R squared told us the proportion of the variance in the dependent variable that's predicted by the independent variable. If that sounds really familiar to what I just told you about the F statistic, then you're paying attention. Good job. So let's go back to the sum of squared residuals around the fit. So in green here, I'm showing you the sum of squared residuals around the fit. And in blue, I'm showing you the sum of squared residuals around the mean, right? And so this is equivalent to our sum of squared residuals on the fit. This is our sum of squared residuals around the mean, or our total variation in the sample, right? And so R squared was this ratio, 1 minus the sum of squared fit over the sum of squared total. And so if you write this out a different way, R squared translates to the variation around the mean minus the variation around the fit divided by the variation around the mean, right? And if we write this another way, it basically says, what percentage of x is this, right? If you wanted to know what percentage of anything was anything, you do this minus the individual value divided by the total, right? So it's the total minus the individual minus the total. And in this case, it's the variance, right? So it's what percentage of the variance is accounted for here. And that's what R squared ends up being. So let's relate this to this new statistic F. So if this is R squared, it would be the sum of squared residuals total minus sum of squares fit over sum of squares total. So R squared is the variation explained by the fit divided by the total variation. So this top is the variation explained by the fit, and the bottom is the total variation. F is the variation explained by the fit divided by the variation not explained by the fit, with a bit extra that we'll get to in a second. But here, right, F is going to be the sum of squared. The top is the same. It's just the sum of squared. It's the variation explained by the fit. That's what this is. That's what this was in the R. That's what this was in the F. But the denominator is now different. Instead of the total variation, now you're dividing by just the variation in the fit, right? And the residuals in the fit are exactly this, the variation that's not explained by the fit, right? The green lines here away from the red line, that's the distance each of these points is away from the fit, and that is another way of saying the variation not explained by the fit, right? Because if all the variation was explained by the fit, all of these points would be directly on the line. So man, these are really similar things, this R squared and this F. And you can calculate your F statistic for a linear regression. And in fact, it has a very specific use for linear regression that I will show you in a sec that has to do with this second part of F, which has to do with degrees of freedom, right? And before we get into what all of these things are, well, these are pretty easy to parse, but generally this second term of F is going to account for the fact that the more variables that you fit something with, the easier it is to get a fit. You're never going to get a worse fit if you add more independent variables to your regression. And so we'll talk about that in a second. But this ultimately rewrites to this. Your F is your sum of your variation explained by the fit here, divided by some degrees of freedom stuff, which we'll talk about, and then your variation not explained by the fit divided by some degrees of freedom stuff here. Okay, so let's go into what that extra is, this p-fit, p-mean, p-fit, and n. So this term p-fit minus p-mean, these p's are degrees of freedom. This is essentially going to be the degrees of freedom between the groups. And here, this is going to be the degrees of freedom within the groups. So here, for this linear regression that I'm showing, there are two parameters in the fit, m, the slope, and b, the slope-intercept. And there's one parameter in the mean, which is the mean. So this will end up being 2 for the slope and the slope-intercept, and this is 1 for the mean. Down here, n is the total number of points, 1, 2, 3, 4, 5, 6, 7. And p-fit, again, is 2, because that's the number of parameters that are in the model that we're using. So that is p-fit. So this accounts for fit, right? The more parameters that you fit with, the easier it is to fit data. So if we had a multiple regression, right, where we were fitting one dependent variable with many independent variables, you would have more parameters in your equation and more degrees of freedom. And essentially, this is accounting for the fact that every time that you add an independent variable into your analysis, you're always going to get a better fit to your data than if you had just one independent variable. If you have two independent variables, even this independent variable is completely random, it's still going to slightly increase your fit. It's going to make your fit slightly better, right? And that might be due to random chance, and because it might be due to random chance, you have to correct for that, and that's what this term here is doing. So F accounts for the random chance that the many degrees of freedom that you have when you are introducing more and more independent variables might be randomly making your fit better as opposed to doing it purposefully. So yeah, so F is like R squared, but it is accounting for the degrees of freedom, where R squared is not, right? R squared would just simply say, okay, I'm fitting my data with 1,000 different independent variables, and now the fit's really, really good. But it might just be that you took 1,000 random variables, and 1,000 random variables will fit anything, because you just have so many random variables that you can weight. So F would say, no. If I took 1,000 random variables, the randomness would allow me to fit at this percentage of the time, and therefore it would throw that out and say it's not significant, right? The R squared might be really high, but we don't care because it's just there's so many degrees of freedom that it doesn't matter. And you notice that it's a denominator term up in the top here, right? And so, well, this is the variation explained by the fit, right? You're divided by the number of degrees of freedom that you have, right? So even if you explain a lot of your variation with your fit, if you have 1,000 degrees of freedom, that number is going to reduce down to be much smaller, making F smaller, right? So in that way, F is going to get smaller when your degrees of freedom in your fit are very large. Okay, and so for this example, since we have M1, M2, M3, so 3 slopes and a slope-intercept for this multiple regression, now we have 4 parameters, right? So p-fit would be 4, p-mean would still be 1, and we ultimately end up with 3 degrees of freedom up here in the top for calculating our F statistic. So this is how we would do it for a regression, but we care more about how we're going to do it for categorical variables. So just like we calculated the F for a linear regression, we can also do it with an ANOVA. And this makes ANOVAs pretty easy. So our calculation for F remains the same. We have our sum of squared residuals total minus sum of squared residuals fit over our degrees of freedom term divided by our sum of squared residuals for the fit. So we can do it for categorical variables too, which is what an ANOVA is. So say we have 3 groups or 3 categorical variables. Each one of them has their own mean, denoted by x bar here. And in this case, these 3 x bars are going to do the same job that the line was doing in the linear regression. So this is the fit for the first category, the fit for the second category, and the fit for the third category. And if we wanted to calculate our sum of squared residuals around the fit, we would do what we're doing here with these black dotted lines, right? The distance from the blue mean for each of the blue points, the distance from the green mean for each of the green points, the distance from the orange mean for each of the orange points, squared would give your sum of squared residuals around the fit. If we wanted to get our total, just like for the regression, we would draw a mean line through all of our points, and this is the mean of all the points in all the sets. And then we would take the residuals around that grand mean, which is denoted by this x double bar, and we'd end up with our sum of squared residuals around the total. And then we plug them into our f, and we just did it. You did f statistic for ANOVA the same way you did it for linear regression. You would be doing it for an ANOVA. So let's cover what the degrees of freedom values are going to be for an ANOVA. So in this case, because we have 3 different groups, the p fit is going to be 3. Our n is the total number of points in our entire set, so here it would be 12. And our p mean is going to remain 1, since there's one line here. So yeah, this is it. For here, it would be 3 minus 1, 12 minus 3, and that would be it. That's how you calculate f. And there's a few other cool mathematical things I wanted to run through with you. So one math conversion here is that this sum of squares residual total minus sum of squares residual fit is equivalent to saying the sum of squares between, right? So this is the sum of squares between groups, which is this top term, between groups. And you can also calculate it by saying, okay, I'm going to take the mean of blue minus the grand mean squared multiplied by the number in the set. So here it would be 10 minus 10 squared multiplied by 4. Then you could go through and say, all right, well, now we have second mean is 12. 12 minus 10 squared times 4, since there's 4 in that set. And then the third one, we'd say, okay, this one has a mean of 8. So 8 minus 10 squared multiplied by 4. So the sum of squares between here would be 32. All right, so you could go through each individual point for the total and for the fit. But if you want to skip to this top term of the numerator here, then you can use this abbreviated formula for sum of squares between. I don't think that there are some ways that you can do sum of squares fit using just the variances, but I think taking the sum of squares is pretty easy. So I'll leave sum of squares fit in the denominator as sum of squares fit. But know that sum of squares fit is also shorthand for the sum of squares within, right? So sum of squares fit, this is the within group variability. So we have a between group variability or a within group variability. So here, you would just go through 13 minus 10, 10.5 minus 10, 9 minus 10, 7 minus 10 for the first group. Then with the second group, it would be this minus 12, this minus 12. Last group would be this minus 8, this minus 8. Until you have the end, you square them all, you add them up. There's your sum of squares of your fit. Plug it into your equation, you have your F statistic. So good. All right, we've got our test statistic. But how do we turn the test statistic, in this case F, into a p-value? We've done it before for a t-test, but we've not encountered an F before. So what is F? So F curves are essentially describing random sets. So if you would have a random combination of points with n total samples and I number of groups, so 10 samples and 10 groups, there would be a specific F curve that you would use for that. And that specific F curve for 10 samples and 10 groups would be the probability distribution of F distributions for random points. So any points from negative infinity to infinity, randomly selected, will give you an F distribution. And then calculate it again, and you get another randomly selected F distribution. And select another 10 random points and another F distribution. And if you keep doing that over and over and over again with lots and lots of different sets of random points, you'll end up with your probability distribution of F distributions, right? And so this is saying, all right, for random points, this is the F statistics that are generated for, infinite number of points or infinite number of iterations you would generate your smooth curves. And so that's your probability distribution of possible F statistics given some number of samples and some number of groups. And you would always look this curve up. There used to be big tables of it. Now R will allow you to generate an F curve if you want. If you select your number of samples and your number of groups, you can generate an F curve and see what the likelihood is of getting any particular F distribution at random. And so then your p-value is going to be the area under your F curve, right? So in this case, it's an F curve with 3 degrees of freedom and 30 and 40, 3 degrees of freedom and 39 total samples. So 36 degrees of freedom. And so you'll have this particular F curve. And then your p-value, if your F statistic was 3.3, is all the area under the curve that is less likely than your F value, right? So the most likely thing is to get something down here. The least likely is to get something out here. So everything in the tail, if you add all of this up, this will give you your p-value. So your p-value is everything that's less likely than your F statistic that you generate. All right, so that's how you go from your F statistic to your p-value. You integrate everything to the right of your F statistic with the F curve that it corresponds to your designated degrees of freedom. Okay, so how does this work in practice? In practice, R does everything for you. There's this ANOVA function. You put your dependent and your two factors in, factor 1 and factor 2, your dependent variable, and it will do everything for you. And in our workshop this week, we'll be dealing with R and that output that it gives. But the output that it gives when it does everything for you is going to be your F statistic and your p-value. And you should know what that F statistic tells you, right? So at the bare minimum, you got to know bigger F statistics. That means you're going to be rejecting your null hypothesis. Lower p-values, that means you're going to be rejecting your null hypothesis. And if you reject your null for an ANOVA, that means that one of your groups is different. You don't know which one, but one of them is. And then there's a follow-up test that you can do that we'll go over in the workshop too, that can substitute for having to do t tests for every single thing, right? It's a built-in thing in R that will do it for you. So this is what an ANOVA is, and this is what it's useful for. I hope you like that it really, it's not so different from the regression and the t-test and everything that we've learned in this course thus far.